This is a short video about the right-hand rule. This is my incredibly messy desk and my water bottle, which is here to demonstrate the right-hand rule. You've been living with the right-hand rule in all kinds of contexts, but maybe you've never realized it. So if I want to open the water bottle and I use my right hand, my fingers curl around the lid and I turn it, and if I put my thumb out, that's the direction that the lid actually travels. And almost all screws, anything with threads on it, obeys this right-hand rule. Sometimes you'll find hardware that goes the other way, and that's called a reverse thread. So to demonstrate again, if I want to close the water bottle, I need the cap to go down. And so if I use my right hand, point my thumb down, my fingers curl in the direction that I need to turn the cap. So this actually comes from a right-hand rule for torque in mechanics, but obviously it also shows up in electricity and magnetism. So let's take a look at a couple of those problems. All right, let's take a look at using the right-hand rule to describe magnetic fields from a straight current carrying wire. So the rule here is that your thumb is going to point in the direction of the electric current. And don't worry about whether we're talking about negative charges moving or positive charges moving. Current is always defined to be positive charges moving. So just find out which way the current goes, and that's the way your thumb points. So you do need to know your left from your right. This one's my right hand. So if I have a side view of the wire, I'm going to point my thumb along the current, and my fingers naturally curl around, and that's the direction of the field. So what we mean by that is the magnetic field is going to loop around this wire, and it's going to loop in the way that my fingers curl. So they are going to go down underneath the wire, back up behind the wire, which I can't really show you, out toward you above the wire, and then down in front of the wire. So if I kind of sketch that, that means they're coming up from behind the wire, over the top, down the front, and then back down behind. And the field kind of forms this like bullseye pattern that is often easier seen using the end view. So let's switch from the side view and take a look at the end view. This is a cross section of the wire, like we just snipped it off and we're looking down the wire. The dot in the middle means the current is coming towards us. It's like the tip of an arrow coming at you is one way to think about it. So get my right hand ready. I'm going to point my thumb in the direction of the current. That means pointing straight up out of the page because the current's coming up out of the page. And then the curl of my fingers is the direction of this circulating magnetic field. So that's the rule for a straight current carrying wire. All right, let's take a look at how the right-hand rule describes the magnetic field from a current loop. I have examples of two different shapes here. So loop 1 is a nice straightforward circular loop. This time I'm going to use my fingers first rather than thinking about my thumb first. So I'm going to curl my fingers in the direction of the current, and in the center of the loop, the magnetic field points in the same direction as my thumb, which is straight up. So the magnetic field in the center here will be coming at us. So I use the dot, like the tip of the arrow, coming towards us. Does the thumb rule still work here like we had in the straight line current? Yeah, it totally works. Check it out. At the top of the loop, the current is moving to the left. If I point my thumb to the left, then the magnetic field curls around that little segment of wire. At the top of the wire, it goes into the page, it comes down behind the wire, and then in the middle of the wire, it comes back out, which is exactly what we saw. At the bottom of the loop, the current points to the right. If I point my thumb to the right and imagine my fingers curling around the wire in the middle of the loop, my fingers come up out of the page. Again, that's the direction of the magnetic field. So we can use that same argument coming to this rectangular loop. We can imagine, or we can analyze each side of the loop separately. So there's a straight wire here with the current pointing to the right. The field then comes up out of the loop. Check that against this right-hand side where the current flows upward. Point my thumb up. My fingers come up out of the loop in the center, so that's consistent. At the top, my thumb points to the left with the current. My fingers come up out in the center, and it'll be the same thing on the left-hand side where the current points down. My thumb points down. This is hard to show. And then my fingers come up out of the loop. So all four sides give me the same result. Inside the loop, the current is absolutely pointing up out of the page. Do I get the same thing using the fingers first method? Yeah, I do. Point my fingers around and bend them in the way that the current flows, and my thumb represents the magnetic field. So thumb first, finger first, it doesn't really matter. There's only one right-hand rule. And so you can see how it applies to straight wires and wires bent into loops. All right, let's take a look at the right-hand rule and magnetic force. So the equation we use for the magnitude of magnetic force is charge times speed times the strength of the magnetic field. But this equation doesn't give us direction, and force is a vector. What we're doing here is we're getting a vector out of two other vectors, velocity and magnetic field. The right-hand rule gives us a way to combine three vectors. We've been doing it with fingers, curling, and thumb. Another way it's sometimes shown is with three fingers, or thumb and two fingers, I guess, all perpendicular to each other. This is like an XYZ coordinate system. I don't like this version. I find it very uncomfortable, but you can use it if you like. So let's take a look at this first scenario. A positive charge, Q, moves with velocity to the right into a magnetic field, which is directed down into our page. These X's are like the tail feathers on arrows moving away from us. So that's how we interpret that magnetic field. So our fingertips will be like the charge. It points in the direction of the velocity. Curl your fingers in the direction of the magnetic field, and your thumb pops up in the direction of the magnetic force. So in this case, I'm expecting an initial force as this particle enters this field that's upward. I say initial because that'll make the particle begin to curl around, and if this field is big, it'll actually end up circling, but the initial force here is upward. Let's see if we can make that work with thumb first and then fingers. It should work. That's not usually the way I do it, so basically we're going to see if I will screw it up here. So I move my thumb in the direction of the velocity, and then I need to point my outstretched hand in the direction of the field, so that's straight down into my page, and then the way that my fingers curl should give me the force. That's upward. So that is consistent. Let's take a look at this bottom one. It's the same velocity direction, same field, but a negative charge. That'll produce a negative Q, and even though I said this doesn't give us direction, the negative on the charge does tell us that the direction we get from the right-hand rule needs to be reversed. So we should get a direction that points opposite here. So let's just redo it. Velocity, and then bend my fingers in the direction of the field into the page. My thumb points up, but use that negative sign to flip it over. So that's how I would get a force that points down. This is a vector. Let's see if I can do it with my thumb. Thumb points in the direction of the velocity. Fingers point into the page. They bend in the direction of the force, but with a negative sign, we reverse it. So that's how I get that. All right, let's just look at a couple of other examples. So what I've drawn here is a curved wire, or like an L-shaped wire, reversed L. It has a bend in it. So the current initially flows to the right, but then it flows up toward the top of my page. This is in a magnetic field that points down toward the bottom of my page. So there will be different forces on the horizontal segment of the wire compared to the vertical segment of the wire. So once again, think of current as charge times velocity, because this current is caused by moving charges. And even though we know there are really electrons moving in a wire, remember we pretend that there are positive charges moving. So you don't need to fuss with a negative sign or a left-hand rule here. Just stick with your straight, normal right-hand rule. Fingers in the direction of the current. I need to curl them in the direction of the field, and so that means there will be a force in the direction of my thumb, which is banging against the table, into the page. So I'd say the force in this region points into the page. So there's an X there. It's like the tail feathers of the arrow. Let's see if I can do this with my thumb again and not screw it up. So thumb in the direction of current, outstretched fingers in the direction of field. Oh, that's awkward. So it points down toward the bottom of my page, and then my fingers curl in the direction of the force. That's still into the page. Now, after these charges round the bend and are traveling upward, fingers in the direction of the current, and then I'm supposed to bend my fingers in the direction of the field, but that's more than a 90-degree angle. The current here is anti-parallel to the magnetic field. They run right next to each other, just in opposite directions. So there's no force on the charges in this area because the field and the current, or the velocity of the charges, is not perpendicular. It's not perpendicular, or at least a perpendicular component. If it's perfectly parallel or anti-parallel aligned, there's no force. All right, final one, this case of two parallel wires. The top wire produces a magnetic field that we can find using the right-hand rule. So point my thumb in the direction of the current, my fingers naturally curl around. So the magnetic field from the top wire points out of the page above the wire and into the page below the wire. I think my pen's dying. I have another pen. So at the location of this lower wire, there's a field from its neighbor that points into the page. So that means these charges now that are moving to the right feel this field into the page, and so they will experience a force that points upward. Check it with my thumb. Thumb goes this way, fingertips point in the direction of the field, curls in the direction of the force, yep, an upward force. Meanwhile, this lower wire produces a magnetic field that at the location of its neighbor is coming up out of the page because the field from the lower wire curls around, so above it, it points up out of the page. So now the charges in this upper wire, as they travel to the right, they feel a force pulling them upward, and so my thumb is pointing down. I know it's kind of hard to see, like this. So these two parallel wires should have forces that pull them together. And that's how I use the right-hand rule when it comes to magnetic force.